Similar to the notes that we took for parabolas and ellipses, we're going to vertically fold this page since we will be talking about two types of hyperbolas. First, let's define hyperbola. A hyperbola is a set of points on a plane where the difference of the distances from two fixed points is constant. Recall that ellipses have the sum of the distances from two fixed points that are constant. So hyperbolas are very similar to ellipses. Similar to ellipses, we have both a horizontal and vertical hyperbola. As we can see here, here is our horizontal one because it opens horizontally, and here is our vertical one because it opens vertically. Let's sketch a horizontal hyperbola, so we're going to begin by graphing the center, just like we did for the ellipses. We're going to find V and V prime, or Victor and Victor prime, by going a distance away from the center. And because it's horizontally, we're going to go to the left a distance, and we're going to go to the right a distance. And that's going to find our Victor and Victor prime. For our horizontal hyperbola, we are also going to go the distance B from the center. We're going to go up B and down the distance B, and we will find B and B prime, or Bob and Bob prime. Finally, we're going to go C distance away from our center, and that's going to give us our focus and our focus prime. Notice that C is larger than the distance of A, so it will be further out from the center than our victors. Once we have done that, we're going to create a horizontal line with our bobs, both at the bottom and at the top. We're going to create vertical lines going through our victors and our Victor prime. And where they intersect is what we call corners of our rectangle. So this corner of our rectangle, this is another corner of our rectangle. If we draw a line, a diagonal, from one end of the corner to the other end of the corner, going through our center and extending outward from our box, what we're creating are asymptotes. So notice we create them by going out of the box to one corner, through the center, through the outer corner, and outside, extending further out. These are asymptotes. To finish drawing our hyperbolas, we also know that we have the latus rectum. So we're going to go to our focus and go half the distance up on our latus rectum, and it should be relatively close to our asymptotes that we're finding. So we do the same thing here. That's our LR, our latus rectum. We do the same thing with the other focus. We go up and we're going to find our latus rectum. We're going to go down half the distance till we get to our latus rectum. And then finally, in order to complete our graph, we're going to start at the vertex, go to our latus rectum, and then towards our asymptote. From the vertex to the latus rectum point towards our asymptotes. Vertex, latus rectum, towards the asymptote. Vertex, latus rectum, towards the asymptote. So that green portion that you see there is actually our graph of our horizontal hyperbola. Notice that when we come to our vertical one, we have the exact same thing. We still started at the center. We went a distance up to get to our vertex and to our vertex prime. And we did the same thing with the B's. And remember, in order to create our asymptotes, what we did is we did a horizontal line that contains our vertex, a horizontal line that contains our vertex, and a vertical line that contained our bob and our bob prime. And we were really truly just interested in those corner values, because when we're making our dashed line for our asymptote, we're going to go from one corner through the center and out to the other corner and extend further out. These are what we call asymptotes. The other thing I want to note is that if we go from Victor to Victor prime, this is what we call a transverse axis. If we go from Bob to Bob prime, this is what we call conjugate axis. And those dashed lines we're calling our asymptotes. And notice, in order to graph, we will start at our vertex, go towards our point of the lattice rectum, and then out towards our asymptotes. Sometimes we're going to find those lattice rectum points are so close to the asymptotes we really don't need them. But one of the things I do want to note, and that's going to be our slope of those asymptotes. And we can easily find them by going from the center of my hyperbola and then going to one of those boxes. So it's going to be the rise over the run, the rise over the run. And that's going to give us our slopes. We can also, that will give me our positive slope, and I can go rise and then to the run to the left, and that will give me my negative slope that we have over here. Continuing down with our notes, we're going to find that we have two equations. We're going to have two equations, one for our horizontal hyperbolas and one's for our vertical. We also notice that we're going to have an equation of the lattice rectum, and it is the same for both hyperbolas. One thing we do want to notice when we look at these equations is how they are similar and how they are different from both the ellipse as well as from each other. Notice that for ellipses we have pluses here, and for hyperbolas we have minuses. Also, we notice that we have x squared first here, so it tells us that it opens left and right like the x-axis. Over here we have the y's first. It opens up and down like the y-axis. The other thing I want you to notice is that a squared doesn't have to be bigger, but it is always written first. Continuing with our notes, we can find important information about our hyperbolas similar to that of an ellipse. We know that our center is HK, and depending on whether it's a horizontal or a vertical hyperbola, we can see that what's going to change are the x values when we're looking for Victor and Victor prime and the foci, if it's a horizontal hyperbola. If it is a vertical hyperbola, notice the y values are going to change for Victor and Victor prime and focus on the two foci. The other big thing to notice is that our equation for our relationship between A, B, and C, the distances, is very familiar to us. That C squared is equal to A squared plus B squared. I also wanted to mention one more time about the conjugate axis and transverse axis. One unique thing that we do not have for ellipses, but we do have for hyperbolas, are these asymptotes. And I notice the equation is going to be in our point slope form, so it's y minus y1 plus our time is equal to our slope times x minus x1. And we're just using the center because we can guarantee that point instead of looking for another point on the asymptote. So notice that we're going to have plus or minus because we have two asymptotes, one with a positive slope and one with a negative slope. And that concludes this video about general information of hyperbolas.